Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this lecture in this particular course on analytical spectral microscopy applications of inorganic compounds and nanomaterials. In the immediately previous class, I was talking about the vibrational spectroscopy, particularly in terms of the Raman and infrared spectroscopy, and towards the end we were looking at different kinds of vibrations, fundamental vibrations that come out, how to understand these vibrations, etc. I will just take you through once again those examples that I have been talking in the previous class. For the water, you have 3 vibrations. For the CO2, there are 4 vibrations. In the water, all 3 vibrations are IR active, and in CO2, and you have one of them is Raman active and 3 are IR active out of the 4, and so you can see mutually complementary in each of this, and that's why it is known as the Raman is water is a poor scatterer of Raman, and you know that is a blessing in disguise. The reason is that most of the biological samples are studied in water. So when you want to study the vibrational spectrum of a biological system like a protein or some kind of a tissue or any of these things, when you study in water or buffer, and there should be a least scattering coming from the medium. The medium is water, and in fact that is true. So therefore the Raman spectra gives a blessing for the biological samples to study better than the infrared, because the water infrared absorption is very strong, and you would see the band will be very huge. Most of the bands will be obscured by the band of the OH, so from the OH stretching. So therefore that the water is basically enemy to the study the biological molecules, whereas the water is a good friend if you are studying by the Raman spectroscopy. So therefore most of the biological things you will go with the Raman spectroscopy. Whenever we come to that, I will go show you some examples. I have also in the previous class shown you these the different vibrations coming from SO2. All these 3 are the IR active. SO3, where one of them is Raman active and 3 of them are IR active. Of course I would like you to practice all that. And the CH4, and 2 of these which are in the symmetric form where there is no change in the dipole moment, they are Raman active, and those where there is a change in the dipole moment, they are the IR active. And you have PTCl4 things, etc. And so the top 4 in this are Raman active, and these bottom 3 are in the IR active. Okay, so therefore you can, by studying both the Raman spectrum as well as the infrared spectrum, you can get a total vibration spectrum. A total vibration spectrum is the Raman spectrum plus the infrared spectrum. Okay, so total vibrational spectrum you will get only then is nothing but the infrared spectrum plus the Raman spectrum, and that is what is total. Of course these spectra are influenced by the infrared spectra is influenced by the combination bands and the overtones, etc. This is another different aspect altogether. I have given a link for you to PCL5. Please go through that link, and so you can see different bands, how they look like. You click here, animation will tell you for this particular band this is the kind of a vibration. Suppose you wanted to look at some stretching vibration, now you can see that, and if you want to see a different kinds of stretching vibration, you can see that. So click this, and if you want to see the vectors, you can see the vectors, how they are orientation, etc. So please do that. For many molecules such kind of a animations are available in the literature, and I recommend you to keep going through that to get a feel of that. Okay, now having looked at the very basics and what are the vibrations are, symmetric, asymmetric, stretchings and bending, rocking, all those things, deformations, they are all coming under the bending category of that. And now let us look at, for a very quick pass through, the spectrometers. So first let us look at the infrared spectrometer, very simple and very easy. In fact, the infrared spectrometer came up into the literature, into the usage much earlier than even many other spectrometers, the NMR and other things. So because of the simplicity which is involved in that. So you have IR spectral radiation source, and source which gives IR spectral, and then of course these are a few optical things which will focus and things like that. And then you have two sets, one is a sample, other is a reference, and your beam is split into the two, one beam going that direction, one beam going through this direction, so that you can get the difference in the spectrum always. And now you're getting out, that is called the transmission. So what you're measuring is transmission. 1 minus transmission is absorption. You can get, so sometimes the spectra are shown as absorption mode. In certain cases, in most of the cases, is shown as a transmission mode for infrared spectrum. And then light coming here, these two have to be basically differentiated, subtracted, and then analyzed. Again, monochromatic grating, and this is what the detector you can call. There's a source and the sample and the detector, and in between you have a lot of optics kind of thing, and this will lead to kind of a spectrum like this. So on the x-axis you have the infrared frequency as plotted, the y-axis the intensity or the peak. Now most often now people are not using simple IR, they are using Fourier transform IR. In the Fourier transform IR, what you will do is you will measure the spectrum as a function of the time and with the pulse that is used. That is called time domain, where you keep changing the mirror orientations, etc., positioning, etc. And then you measure the constructive, destructive interference, and then you store all these in the form of the time scales, time domains, and then you convert this into the Fourier transform into the signal with the frequency domain. And you can add these things, a large number of scans, and therefore you can get the signal to noise ratio is greater. And the signal to noise ratio is greater when you, now if you have signal to noise ratio is proportional to the square root of n is a number of scans. In some cases they call it as a transients, number of scans. So if you can make some 100 scans, square root of 100 is 10, you get a 10 times better the signal to noise ratio. So that is the kind of thing. So when you increase the number of scans and then measure, then you will get a much better square root of n level of the signal to noise ratio. So this is for the infrared, very simple. In case of Raman, it is not this one, because you are not measuring the transmission, you are measuring the scattered light. So in the scattered light, you have you use a laser, as I mentioned, that you require a very high intensity beam, okay, and then the sample, and from the sample you have the radiation coming scattered in all directions. But if you take this is the path where you require, this path is the 90-degree angle, that is the source, the sample and the detector. So these three angle is the 90-degree. So the 90-degree scattered radiation is more in the Raman's direction, and which is a better, which has other things less, other scattered. So of course these are all the optical modulations, modifications, and then resolutions, and the detector finally come to that. So basically this angle what you refer to is a 90-degree angle. So it's much different in terms of the instrumentation. This instrumentation came much later, at least 30-40 years later to that of the in terms of the instrument. Of course it was shown by Raman in 1928 paper itself, or earlier than that. So that's not he has not used the laser, because the laser was not developed at that time, and it was shown with a conventional lamp, but then these things were developed much later over that. And many large number of techniques of the Raman related were there, something called resonance Raman, surface enhanced Raman, all these. So the Raman spectroscopy today is a very broad, because you can study biological samples in aqueous, you can study inorganic samples of the surface, the heterogeneous catalyst, all these kinds of things where a lot of other matter present, and then no problem at all in this. So we have looked at some basic parameters of the spectrometer. Now let us look at, now move to one level next, and we are talking about the vibrational frequencies, and we also talked about the fingerprint. We also talked about the group, the functional groups can be identified. So please look at this particular slide, and these frequencies are dependent on what? Dependent on, I have already talked to you about the frequency of the thing is proportional to square root of k by mu, reduced MOF and force constant. Therefore, you should see the what are the atoms involved in that vibration. The vibration is stretching or bending or what it is. So how much variation in the mass can come, mass can affect that one. And the second thing is the force constant, what to strength these are. So it could be in the stretching, this bending, the force constants obviously will vary depending upon the vibration, and this will vary with single bond or double bond or triple bond. So if you have a CC, C double bond C, C triple bond C, etc., C single bond O, C double bond O, C triple bond O, etc., all these will vary. So therefore your whole thing will depend on the bond strength or force constant is called, and the reduced mass and the type of vibration that you are looking at, the energy. So for a little while, please focus on this side. You have, this is the OH, NH region of stretching between 3500 plus or minus 300 either side, and this, and you have a CH stretching around 3000 range, and these are all for single bond OH, NH, CH, etc. Then you have a nitrile or a carbene, which is multiple bonding things will come here, is not shown in this particular spectrum. And the double bond like C double bond O, C double bond N, C double bond C, they come in this particular region of 1600, and down little lower energy, C single bond O, C D single bond N, then C single bond C, which is between 1300 to 900,000 range. Then comes a lot of rocking is much low energy, the bending is low energy, stretching. So stretchings come on this side, bendings come a lot on this side, and then for the same molecule you can compare that, but different molecules bending could differ. The new CO is stretching itself comes here, so these bendings will go much lower. So always stretching frequency nu of stretching is greater than nu of bending, which is greater than nu of rocking vibrations, etc., for the same molecule. Don't compare for the different types of molecules, etc. Now you got an idea. This region, of course, this is a region which is also overlapped by a lot of combination and overtone bands. Combination means some of the earlier bands who have a similar symmetry can combine and show. Suppose you have one new one here, new 2 here, you can have new 1 plus new 2. So this is 1400, this is 1300 to 2700 you can have. So that kind of things are called combination. Or this twice of that, and with a little difference because they are harmonic. So if it is 1400 in twice 2800, so around 27, 26, 50 you will find here, which is as a overtone. Those are we are not much talking about. So therefore this region will be much less used in terms of the functional group, the identification, but for some other reasons, when you change the isotope, when you have a water, when you have OH, when you have one NH, when you have a CH, then again this region is useful. For other things, these regions are useful. For double bonds, triple bonds, this region is useful. So very gross way of talking about these things. Now mostly that is the organic type. You can look at the inorganic type. So MC bonds, vibrations come somewhere in this region, 500 below, etc. And the CS bonds, Cn on this side, which you have seen in the previous case also somewhere here. You've seen the M, this simple CO, not the MC, it's a simple CO. A lot of carbonyl structures are studied initially before the structures are known by infrared spectroscopy. In 50s and 60s, very well established. Many of the carbonyls which were synthesized were studied by transition metal carbonyls, other things studied by infrared spectroscopy, and a lot of information was derived based on that. Later on, confirmed by crystallography and other things. Okay, MC will come below 500, 600 kind of thing. Mn again below 500 and thing. Simple NH3 in the range of the 1500, 1600, the bendings, and then rockings will go below 1000. The rho with the R is called the rocking, delta is called the bending, and these kind of things. So for example, Mn again here. So different NO2 groups, stretching NO2 comes here. So therefore NO2 group can be identified as a functional group within this range. So and then CO stretching somewhere around this region, and then when it's bound to the metal, etc. No, sorry, this is the C. This is C double bond O. This is C triple bond O. Carbonyl will, carbon monoxide things come here. Sorry, carbonyl will come here. The C double bond O, and that stretching and other vibrations. When the carbonyl couples with the NH in the amides, there are different kind of vibrations coming. Amide 1, amide 2, amide 3. So they all come starting from 1600 down, not higher. So the nitrate kind of things, water we have seen stretching comes into 3500 plus or minus. Again, hydrogen bonded water, non-hydrogen bonded water, extensively hydrogen bonded water. So all these things will change in their stretching vibration. Then their bending comes into 1700 here, etc. Huge range is developed and used into that. Both the ligand part as well as the metal ligand kind of things come here. So the metal being heavier, the metal nitrogen, metal oxygen, metal sulfur, they all come much lower. Metal sulfur will come much lower than the metal nitrogen, metal oxygen will come between 600 to 400 range, in that range, whereas metal sulfur will come to lower than that range. Metal other things will come much lower than the metal halides, which come again below 300 or 400, etc. Some examples we'll see as we keep moving across. So just as to pass by, and this is a compound of CS2CrCl5 with water, and the spectrum is mainly dominant with the spectral news OH, and the bending of the water and the rocking of the water. A little bit of metal halides, etc. will come much lower, so that is why it is not seen here. I hope you are looking at the spectrum and the slide. So barium sulfate, SO, both symmetric and asymmetric. Asymmetric will come higher energy, symmetric will come lower energy. Then OSO, that is the bending kind of things, and so symmetric, asymmetric you can see. So fully that sulfide you can make out. Similarly sulfates also one can make out, etc. So here KMnSeO2OH. So again you can find a lot of OH, the other things, stretching, bending, and the SeO things, etc. SeO3 vibrations and the rocking vibrations and bending vibrations, they all come here. And this is another extension of that compound you can just sit and look at. So primarily you will see whenever you have the water is dominating, and your metal related ones come below 1000, below even 500 metal related one. Some groups like sulfate, nitrate, perchlorate, these come within 500 to 1200 range, etc. that you can see all of them. Now let us spend a minute or a couple of minutes on the carbonyl compounds. As I mentioned, the metal carbonyl compounds have been studied way back in early stage when there are no other tools were available for structural, and then reasonably well established based on that. Later on, the structures were confirmed to be correct, most of the cases, and after the structure. Carbon monoxide can bind to the metal, straight MCO with a single bond kind of thing, or the CO can be bridged between the two metals. The CO can be bridged between two metals, while one metal is really forming a sigma bond, the other metal is forming a somewhat weak bond. You can also have the one other metal to the C, other metal to the O, weak of course, or The C is to one metal, O is to the other, like linear fashion. So variety of ways that the carbon monoxide, in fact compounds, the chemists have synthesized compounds coming with all these kinds of structure, with all these kinds of structures, and many more intermediate levels are not shown here. So this is called the side-on bridge, end-on, end semi-bridge, end-on bridge, terminal and linear, all these kinds of things. So how will the infrared will help? The infrared will help, the formula is the same. The formula, what I mean is the principle is the same. So the CO bond strength, how it is varying in this and in this and in this and in this and in this. Okay. So one of the factors is the sigma bond, and the other factors is the pi. If there is a pi electron are pushed from the metal to the carbonyl, then the CO to the will reduce, and the MC of course will strengthen. So you can see both MC bond stretching vibration will be greater when you have a MC bond order is this one will be less than MC, where the bond order is a little bit greater. Similarly, the CO versus the CO, it could be a little smaller, or it could be even double bond itself. It could be even just the simple double bond itself in this. So therefore it is the strength of that bond when it is bound by these is the one which determines. So don't think that carbon monoxide will show only one band depending upon its binding. So nu when you have like this, it will be greater than nu when you have a third bond is weak, and nu which is greater than nu when you have only double bond, and then greater than nu which you have bond, and nu where you have a single. So this. So this all depends upon how this CO is bonded to the metal in various ways, and that is what you are looking at. So I hope now the basic fundamental concept of this is understood. Okay. So if you have a terminal and without much the pi character being shown, then it will come higher actually. So free is 2140 range, and this will be less than that, but 2100, 2050 range when there is no pi interaction from the metal, and when the pi interaction with the metal comes, it will start decreasing the frequency. That is why you see a lot of range 1850 to 2125, almost 300 wave number change. Centimeter inverse is also known as wave number. Okay, so that much the thing. That's one way. So it is not that all metal ions, when it is terminally bound, the frequency will be the same. No, because the metal, whether they are electron rich, whether the pi donors or the pi acceptors, all these kinds of things, all are sigma donors, but only the pi which matters. And this is I explained to you in some other context, in this particular course in earlier. Now suppose you have a bridging, the two other metal and another decrease in that range, or three of them triply bridging also possible. So M1, M2, M3, so this is carbon monoxide, so that it will go further down, etc. So if you just look at there is no pi character playing a role, only the bridging is playing a role. Terminal will be the higher frequency, the doubly bridge will be the lower frequency, triple bridge will be the much lower frequency. So now if you sit and look at these things, you will understand the metal character also in these things. So you can see the NiCO4 and FeCO5 will show two of them, and chromium carbonyl and rhenium decacarbonyl, dirhenium decacarbonyl. You can see some of them lower, some of them higher, and the Fe2CO9, some bridging is there. You can see much lower than 1900, 1800 range. So that means bridging is there, and AgCO plus. It's a little bit higher side, 2200 as compared to even the free. So how can it be higher? Because you're pushing, this is a positive charge, you remove the electron. So when you remove the electron, you will remove from the antibonding orbital. So that means bond order will go up. If bond order goes up, means your frequency goes up. So that is where 2200, you can see that. And copper CO2 plus, again higher than this. So when you have the plus kind of things, you can also get higher one as well. and if you have other modes of binding, you can get other bands. So both ways. So on this side you have the distance will vary. So the stronger the bond, the shorter the distance, the weaker the bond, longer the distance, shorter, longer. So strong and weaker, and that is what we have shown by 3 bonds, 2 undotted and 2 1 undotted and 1. So this is different. Okay, so these are all the kinds of things that, so examples are shown here for Cr2CO9 plus. So something coming in the higher region, because of the positive charge that you have, one electron is removed from the system, and therefore that will strengthen. And there are other kinds of bonds, carbonyls, the terminal ones and the bridge ones. The bridge ones are coming lower, and this kind doubly bridge will come somewhere here, and these are the things. So for the titanium oxy kind, mostly here, and this one which is CO, which is like this kind of a binding, this kind of a bridge. So this is this bridge you can see, and that is what is coming over here. And in this Ti2CO9 plus, this is not Ti2O but Ti2CO9 plus, you have the bridged one, a terminal one, and of course this is mu oxo, and one more carbon, this one, which is somewhat similar to that. So you got the things like here and one additional here because of these bridge one and the terminal ones. So the terminal ones, the bridge one, the linear kind of, they both C and O are bridged, and the only bridged kind of things. So similar kind of things can be explained for this as well, the CO2 CO8 plus. So I hope you got some idea as how these should be looked at. So you have to look at the carbon oxygen bond strength, bond order. There is nothing to look at the use mass, etc. Let us look at some example of coordination complex of this ligand, which is called the vanillin salicyl hydrazone. Kindly look at the slide, please. And this complex with iron, this complex with the nickel. The iron complex is this way. It acts like a tridentate ligand, then 2 of the chlorides, 1 of the water you have here. In case of nickel, this acts as a pentacoordinated one here, and this bridging, and this pentacoordinated thing here. So different. So this compound is very different from this compound. So this metal chloride you can easily find out from below 350, 400. It's not shown here, but you can find out that as well in the 4IR, that is called 4IR. So if you look at the ligand bands versus the metal complex bond versus the nickel complex bond, immediately you can say that the ligand is complexed just by comparing, not with the values, etc. Looking at the spectrum of this, looking at the spectrum of this, you've done a iron salt added and isolated a complex color is also evident. That means complex is formed. And if you look at the infrared spectrum, the first thing impression that you can see is that this is a comparison of the ligand spectrum versus that of the complex spectrum, and say that the complex is formed or complex is not formed. Okay, that can be, or whether it is an iron or nickel, again from the color followed by the bands that are coming up. So this has got bound water, bound halide. So the bound water things can also be seen. Here also there is some bound water is there, some ligands are still there, and so therefore you get with that. And you have other CH, other vibrations are also there. CH comes from most of these are coming from the sp2 kind of a region of that. So if you look at that new NH, yes, and the ligand 3111 and new CO 1669, in the iron complex 1634, and in the nickel complex 1509. So you can see that the new CO band is changing from the ligand to the iron to the nickel. That means it's binding. So you can see that this one is binding and these ones. See, this here, yeah, sorry. So this is here. So binding that, not this one, but this one, CONH band. So you can see that the ligand, the metal ion is bound, or ligand is bound to the metal ion through the CO. So you can also see the CN stretching 1557, and here is a 1551, and here again 1509. Again CN vibration frequency will vary slightly as compared to the these ones, and that's what we are seeing, 57 to 51 to 1509, So those are, so like that, by comparison of these individual vibrations, you can come out with the binding, these complexation, and the ligand is present in that, but bound because of the small changes that you find as expected because of their bond order changing, etc., etc. Okay, so that is where we have looked at the aspects relevant to the basic concepts, how these infrared and Raman, how do one understand the principle, what is the instrumentation, then the modes of vibrations, and then if you start looking at different group frequencies, etc., how you can identify them. And in inorganic, you always compare between the ligand and the complex spectrum, and in fact these are done much earlier, how carbonyls can be studied, etc. So we have a little more travel to go for maybe a couple of more classes, and by start looking at different examples and comparing these spectra, both using infrared as well as the Raman, and together. And then for the inorganic complexes, coordination of course complexes, inorganic species, and the nanoparticles, nanocomposites, and bioinorganic examples. So all these we will be looking at in the couple of more classes coming up before we close the vibrational spectroscopy topic. Thank you very much.